Well, a very good afternoon, and I can today say a very warm welcome from a sunny Johannesburg. A special welcome to Bite-Sized Corrosion. It's absolutely wonderful that you've been able to join us today. We're going to be having a very short 2-week conversation where we're going to be looking at concrete and concrete corrosion. Now, if you don't know who I am, my name is Vanessa Seeley-Fisher, and today I'm joined by Neil Webb, and we'll be going through a few discussion points about corrosion and concrete corrosion. Let's get started with today's discussion on concrete and also reinforced concrete. So we'll be talking about the corrosion protection of both concrete itself and reinforced concrete. I think we're all very familiar with the description of the city being a concrete jungle. I know Neil found an interesting photograph. And I thought, Neil, it would be good to just start talking about what is this thing called concrete? Let's discuss it in a little way, shall we?
We're very familiar with our concrete jungle, and you can see there we have concrete skyscrapers, we have concrete bridges, we have concrete facilities associated with a harbor, and concrete is in our face all the time. And concrete's been around for a very long time. Concrete itself in various forms dates right back to Roman times. Reinforced concrete came about, depending on which source you use, sometime in the 19th century. In South Africa, we may be at the bottom end of the world, but we've had concrete around for a long time. There's a picture of a tunnel with a date stamp of 1929, which is nearly 100 years old, but it's also quite some time since concrete was developed. You may well say that we're going to talk about the corrosion of concrete, but you can also argue, well, does concrete corrode?
It was going to be my question.
So if you look at one of the definitions of corrosion, it says it is the deterioration of a material as a result of a reaction with its environment. So if concrete reacts with its environment, you could then say it's corroding. But I suppose perhaps the more common usage is the word degrade or degradation of concrete. Concrete is a fairly complex material, and this photograph shows you that your concrete structure is a mixture of stone and sand and cement, which you can't actually see, except that in the cement and sand paste that's in between the stones that you can see in the picture, that represents the aspect of the material that is perhaps more susceptible to degradation. We're not going to talk about the alkali aggregate reaction that the civil engineers get involved with, because that's an internal problem. We're going to talk about the reaction of the concrete with its environment.
I think that's been helpful, Neil. And when we talk about aggregates and so on, that obviously is referencing the stone components. Now, from my dark distant past, I remember my father telling me to keep the concrete wet so that it gets really strong. And presumably that's because of those very chemical reactions that you spoke of between water and the chemicals within the cement. But if you think about its uses, surely concrete is also waterproof to an extent.
Well, yes, definitely. You only need to look at a dam to see that concrete withholds water. And we often see concrete farm dams, and sometimes you see stuff oozing out of the side of the dam where it has apparently leaked. And part of the issue, of course, then is that concrete is somewhat porous. And when it is inundated with water, like in a dam like this, the cement paste becomes saturated with water. The pores in the concrete are filled with water. And essentially, it does become a water retaining structure. The structure under construction here, you can see, is probably a combination of reinforced and mass concrete. The wall itself in this particular situation is mass concrete. The intake tower that you can see on the left-hand side of the photograph over here is a reinforced concrete structure. And if we look first at the behavior of the mass concrete, the concrete is resistant to the effect of water, provided the water itself is not aggressive towards the cement aspect of the concrete. So we're talking about lime being one of the principal reactive materials. It reacts to form calcium silicates and aluminates and all sorts of very fancy things like that. But sometimes the water itself is aggressive to that particular aspect, soft waters in particular. And here you can see what has happened over a fairly long period of time, where the cement paste has been dissolved away in between the individual pieces of the stone aggregate that are shown up quite well in this photograph. This photograph actually is of a spillway in a dam, where the steel strip in the middle is a stainless steel bed where the seal of the dam gate sits. And when the gate is open, the water rushes through there, and you can see the way it has both worn and dissolved away a certain amount of the concrete paste that acts as the glue, if you can call it that, the cement, excuse the pun, between the actual aggregate pieces.
So to stop that concrete corrosion, as it were, perhaps apply a coating?
Well, yes, and it's not perhaps used very often in dams, but there are many structures where we can coat concrete. And one of the challenges in coating concrete is the actual nature of the concrete itself. And if you look at this photograph, again, you can see that there are voids in the concrete. These are almost impossible to prevent. You may well have seen people working on casting of concrete, and they have those high-pitched, very noisy vibrators that are used to endeavor to prevent the retention of air in the concrete. You can see micro cracks in the concrete, all of which are a challenge if you now want to coat this material. And here is a photograph of that same concrete surface where somebody attempted to apply a coating, and you can see that the coating has hardly even adhered to the underlying concrete. And in order to get your coatings to adhere to the concrete and provide the protection that is necessary, we often need to use penetrating primers, one of the most common ones being an epoxy. We spoke about epoxies in one of our previous series. And epoxies are very good at penetrating into that matrix and providing an anchor for subsequent coatings to adhere to. The problem of coating concrete as opposed to coating steel is that concrete is actually a chemically active substrate. We know that it has a very high pH because of all the lime, and many coatings do not like adhering to a high pH surface. Making soap means you mix lye, which is an alkaline, with fat, and you get soap. And soap is a really, really good disbonding agent. So if you put the wrong material onto a concrete surface, you'll end up with a layer of soap between the coating and the substrate, and the coating falls off.
Yes, but you have a clean concrete surface.
Oh, for sure. For those of you who've done home coating operations, may well have come across that term called alkali-resistant plaster primer, because plaster, of course, is just concrete without aggregate in it. So we've got to be very careful about how we apply or prepare the surface of concrete for coating. Here's a photograph of a situation where that preparation was not done. And you can see the coating is just lifting off without any real adhesion. Looking more closely at this situation, there's a thin layer of what we call latence on the surface of the concrete, as indicated by the cursor. And that latence is a cement-rich layer. It's very weak, it's very porous, and you have to get rid of that if you want even your epoxy penetrating primers to stick, because without removing that, again, you just land up with mass delamination. That's the surface that you want to coat. And as you can see, it's fairly rough. So again, thin film coatings over concrete can be a challenge, and you need to make sure that the coating that you're going to be using has enough of a build to cope with the rough surface that is created when you expose the underlying aggregate of the concrete.
So you're basically applying all the standard coating considerations to the concrete surface, just as you would if it was a steel surface. There are obviously different considerations, but the same surface preparation, ensuring that you've got the correct coating for the job.
Absolutely. And we not only are dealing with atmospheric conditions, but often we have concrete structures that are used to provide chemical dams, if I can call it that. So in the parlance, it's known as a bund. It's an area where the tank that contains the material that you're dealing with, if it fails or leaks or for whatever reason, you need to prevent that liquid from flowing out into the environment, never mind what other damage it may cause. And you can imagine if you allow sulfuric acid to come into contact with concrete, well, you're going to land up with no concrete. And not only sulfuric acid, here's a situation where we had concentrated caustic in contact with the concrete. It destroyed the concrete, but in this case, the reinforcing came off scot-free because the caustic actually passivated the reinforcing. And you can imagine that we need fairly robust systems to be able to protect these situations. And typically, we would then line the concrete surfaces with either acid-proof bricking or tiling. The interesting aspect of this application is that the acid-proof bricks and tiles, they resist the chemical environment, but they themselves do not protect the concrete. They merely provide physical protection. And underneath that bricking or tiling, you've got to have a membrane which prevents the reaction between whatever it is that you're working with and the underlying concrete. In this case, you can see that the underlying bedding that was used for these tiles was not very resistant to whatever was in this particular application, and it has just dissolved away and disappeared, and the tiles fell off. There was an interesting case many, many years ago when I was involved in the mining industry where we had in the gold mining, it was combination gold and uranium plant. The gold plant uses acids. The uranium plant uses organic extraction materials. One of them is known as raffinate, which is a paraffin-based material. And so the bunds were designed according to their systems. Somebody got the piping wrong, opened the wrong valve, dumped the raffinate into the gold system, and the raffinate got hold of the butyl membrane that had been put under the acid-proof tiles, butyl being very resistant to acid, and the butyl swelled by a factor of 10 or whatever it is, and the tiles came climbing out of the bund, very spectacular fashion, much to the distress of the plant engineer.
I'm sure he wondered what ghosts had gotten into the plant overnight.
Yeah, well, as the consulting engineers on the project, we got one very irate phone call, as you can imagine. And then when we went to site, well, he said, actually, it's your plant operations. And that's actually a very pertinent design factor that should be taken into consideration, is that you don't only design for normal operations, but you also design for upset operations.
Exceptions. Yeah.
But nobody actually foresaw that the upset could be that drastic that they would dump the uranium process into the gold circuit.
Oh, goodness. I'm sure that's a conversation for another day as well. Neil, you've mentioned about how we can stop the concrete from corroding or degrading either by some sort of surface protection or a coating, possibly an additive. And concrete is obviously extensively used because it is so strong, except of course when it isn't and it breaks. Can we explore the strength of concrete for a little bit?
Yeah, well, we know that concrete is a basically strong material, but the strength of concrete is in compression. So when you put a load on it under compression, it is extremely strong and rigid. However, if you subject concrete to tensile stress, in other words, you stretch it, it's not like rubber. It does not stretch. It cracks and breaks at a very, very low value. So for example, if you had, say, a 40 MPa compression strength concrete, you might be lucky if you got 4 MPa in tension. Okay. And a structure like a bridge, for example, has both compressive and tensile stresses in it. The only way then that these structures actually stand up is that they are composite structures, composite in that they comprise more than one material. It is concrete plus steel reinforcing. The steel reinforcing, it provides the tensile strength, which prevents the concrete from cracking. So there's a lot of design that goes into that. And the reason why the steel works so well in these situations is because the concrete is naturally high pH due to its lime content, which then prevents the steel from corroding, provided the concrete itself remains high pH. And there are a few things that can destroy that naturally protective environment. And that's kind of what happened in the industry initially in the 1960s, where in the Northern Hemisphere, England, Europe, North America, the structures froze over in the winter. And one of the best ways of getting rid of ice on the roads is to spread salt onto it. And that salt gets into the concrete, and the chlorides then destroy the passive nature of the concrete and allow the reinforcing to corrode. And once the reinforcing corrodes, you then have a real problem. And so since the 1960s, we've had a lot of work done internationally on now how to prevent the reinforcing from corroding. Reinforcing is embedded in the concrete, and we've got to keep it in its passive state.
That is very interesting. Oh my goodness. Okay.
Yeah.
It doesn't always stay that way.
It doesn't always stay that way. So there are a number of things that can cause the concrete to lose its protective environment for the steel. One of the better known ones is chloride ingress from salts. It can be just from being exposed at the coast, and the chlorides penetrate into the concrete. So of course, if you can improve the condition of the concrete, in other words, increase its impermeability or decrease its permeability, then you're going to extend its life, because then the chlorides don't soak into and permeate through the material. This particular example that you can see in the photograph actually was acid mine water that penetrated into the structure from the mine structure. It was a conveyor structure being washed down with mine water all the time. And another situation that happens is carbonation, where carbon dioxide from the atmosphere reacts with the concrete very slowly over a long period of time, but it can also destroy the passivity of the underlying steel. And when the steel is no longer passive, it corrodes. When steel corrodes, it has a volume increase of somewhere between 7 and 10. And so 0.5 millimeter of corrosion of steel will cause the concrete to then crack and delaminate.
The fact that the steel expands so much during corrosion, I can understand, puts huge pressure on that concrete. But Neil, just rolling back a little bit, when we talk about corrosion of steel, we often use potential to ascertain whether that's corroding or not corroding. Then surely potential can be used as an indication that spalling maybe is not even happening yet, but imminent. Is that an option?
For sure. If you consider a typical reinforced concrete structure where the outer layer of reinforcing is corroding, as you can see here, before this actually happens, the pH of the concrete around the steel will have changed, the potential will have changed. And if we were to plot the potential of the reinforcing and also look at perhaps the chloride levels, you will see that there is a significant increase in chloride content in the area that has got the problem. May have been a pre-existing crack, it may have just been a piece of porous concrete, may have been an area of low cover, anything like that. And you get a corresponding change in potential. So you can see, if you look on the right-hand side here, we're plotting potential of the steel with respect to the concrete, and we can measure that. And there's actually an ASTM standard that allows you to map the potential of a reinforced concrete structure to determine whether or not you are about to get corrosion or not. And this is often used to demarcate areas of repair. So if we look at this particular situation, there's now a conventional repair. The corrosion of the rebar was not too worse. So we chopped out the concrete, put in a nice high quality concrete patch, and
yeah, we've just moved the problem.
We've just moved the problem to the edge of the patch. And those of you who have been involved in conventional concrete repairs may well have experienced this, that you go in, repair a patch, and 2 years later, it cracks again next to the patch. And you just carry on and carry on.
Well, I think it's an interesting observation that you've got rebar that can corrode, because as soon as you've got the fact that it can corrode, you've then got the possibility to stop the corrosion, actually. And if you can measure the potentials with mapping, then maybe we can also consider putting in cathodic protection.
You took the words out of my mouth, because actually that is the subject of next week's discussion. And we're going to be talking about how one can use cathodic protection. Cathodic protection is not the only way you can do it, but it is certainly one of the more effective ways of addressing areas of concrete degradation where we already have degraded concrete, and we need to then prevent it from corroding further. We're looking at preventing the reinforcing from corroding in this particular case.
Well, I think we can almost leave the discussion there. I just want to say thank you to everybody who did join us this afternoon. I hope that it's been something that's either triggered some more questions in you to challenge the way you're approaching your challenges, or whether it's been of interest and something you've learned from. Whichever the reason, we really thank you for taking time out of your afternoon to join us. Thank you so much, and have a wonderful rest of the day.